Hello everyone, welcome to video lecture series of Design of Steel Structures. We are going to start with unit number 6 B part, Design and Analysis of Industrial Roof Trusses or Industrial Buildings. So already in this particular unit number 6, we have initially in A part seen what are gantry girders, what are the requirements and design procedure for gantry girders, and in the second or B part we are looking after industrial roof trusses design and analysis. So these particular industrial buildings are low-rise structures. The characteristics of industrial buildings is nothing but this is a low-rise structure, and because of their low height, lack of interior floors, walls and partitions, this is the characteristics in case of your industrial buildings. If you consider example of regular reinforced concrete structures or frame structures, interior floors are there, and usually the building is multi-storied kind of building, while in case of industrial buildings these are not multi-story type of structures. Usually very less number of interior floors are there, that may be somewhat one or two number of floors, or in many cases it is only covered with triangular type of formation of roofing system, covering with roofing type of material, either GI sheets or AC types of sheets. So these trusses are triangular formations of steel sections in which members are subjected to essentially axial forces due to externally applied loads. So the loads acting on this particular roof trusses, initially the gravity loads are acting, and again secondarily the wind forces are acting on the truss elements, and all these forces acting are axial members or axial forces. Either it may be axially applied tensile force or axially applied compressive type of force, and according to these forces only the members are defined as a compression or they are defined as a tension type of member. Usually this triangular formation is made up of single angle or double angle sections connected at particular joint according to the geometry of truss. So depending upon the span requirement, the type of truss selection is done in case of your industrial buildings. So usually up to less span up to 6 meters or 8 meters, usual trusses like queen post or king post type of trusses are adapted. But when the span of your building is going to exceed by 10 12 meters up to 20-25 meters, in that cases different types of roof trusses are usually adapted for the design. So the selection of type of roof truss depends upon the span. So initially we'll start with the members of your roof trusses or components of your roof trusses. So in this particular figure you can understand is the cross section of fin type of or front elevation of fin type of roof truss. So initially we'll see the first component, and that is defined as your principal rafter. So the definition of principal rafter is it is a top chord member of roof truss subjected to only compressive force due to gravity loads. So gravity load in case of truss calculations are nothing but acting vertically downward, and usually dead load and live load are the forms of your gravity load acting. If usually the purlins are supported on this particular nodes are nothing but these are your joints, and at joint location only we are providing your purlins, so that your principal rafter will be subjected to only axial force. Otherwise if the purling is supported at the intermediate, your purling will be subjected to certain your principal rafter may be subjected to certain bending moment also because of purling. So usually we are adapting the connection or joints, at that point only we are going to provide our purling sections. Then next is principal tie member. So this inclined member we are observing is a principal rafter member. Below that this particular horizontal member, so this horizontal member is called as your principal tie. So the lower part of roof truss is known as principal tie, and it carries only tension. So because of gravity loads, rafter carries compression and tie carries tension. So these are the two basic actions and two basic members. Compulsorily your tie member is a horizontal member connecting your column to column, while in case of your principal rafter it is an inclined member, and it is starting from one end of column and reaches up to the ridge of your building. The next important component is your strut member. So the members of roof truss other than rafter and tie, the members which are other than rafter and tie and subjected to compressive force are termed as strut, while if the members are other than rafter and tie and subjected to tensile force, this will be coming under the category of sling type of sections. So other than rafter and tie member, if the force acting is compression, it will be called as strut member, and if the force is tension type, it will be called as sling type of members. The next member is a purling member. So purling members are nothing but these are your purling sections, and purling sections are acting as a support system for your roofing material. So intermediate load between two individual trusses is usually carried by your purling, and that is transferred to your rafter member. The next is the bracing systems. So members of roof truss which makes it stable for accidental loads due to plane loads or lateral loads is defined as your bracing system. So usually this bracing system either may be provided in vertical direction, inclined direction, or horizontal direction, depending upon the location for provision of your bracing system. Usually your bracing system may be there in case of your columns, it may be provided in case of your trusses, or it may be provided in between your purlings. So either it will be provided for uh, a channel section, intermediate of your channel section as a purling cross section, or it may be provided at the tie level, that is horizontal, or in some cases your columns may be tied. So likewise the classification of your bracing system may be either it may be diagonal type, it may be X type of bracing system, or it may be eccentric type of bracing system. Now type of roof trusses, already we have discussed this. According to the requirement of your spans, your roof trusses are classified as Pratt type of truss or Howe type of truss. So you can understand the nature of change of your member orientation in Pratt truss, in Howe truss, and Fink type of truss, fan type of truss, fan Fink type of truss, and mansard type of trusses. So these particular arrangements are essentially important, and the standard geometry is given likewise only, and based on this only your design is going to be there. There is the differentiation of this number of chords in case of rafter and tie member. Here you can observe that in case of this Pratt trusses only 3 or 4, or in some cases depending upon the span 5 number of your component parts will be there, while in case of Fink truss compulsorily 4 parts are there. In case of fan truss that is going to be only 3. So likewise the total top chord will be divided into number of components parts or chord lengths according to the design. So these are the type of trusses. So usually spread truss and Howe truss are adapted for a span greater than 15 or 20 meters. Fink truss near about up to 15 meter. Fan truss is also up to 15 meter. Again compound Fink, a mansard or Fink fan type, these are adapted up to 12 to 15 meters. So likewise the selection of type of roof truss. Now important is loading or actions acting on your roof trusses. Already we have seen the first classification, that is your gravity loads, and gravity loads are dead load and live load. An important third factor which is the deciding factor for the design is your wind load. Now loads of the roof truss, in that first dead load, it is subjected to dead load, and dead load is nothing but it is a self weight. So dead load of the roof truss includes weight of the roofing material, purling, bracing, truss load. The unit weight of different material are given in IS 875 part 1. So usually for this design process 875 code is to be adapted. For unit weight of material 875 part 1, for live load calculation 875 part 2, and for wind load calculation 875 part 3 is to be adapted. So usually an approximate or empirical formula to calculate your dead load of roof truss is given as span divided by 3 plus 5 into 10 in Newton per meter square. So it is a area load, total span, that is span of truss, divided by 3 plus 5 multiplied by 10. This is the approximate formula adapted. In case of your bracing system, it may be adapted or assumed between 12 to 15 Newton per meter square of the plan area, that is load of bracing. And the purling, design of purling based on the roofing material load is already done, therefore the weight of purling can be considered for design directly. In some cases it may be considered directly, or you have to take it separately. So likewise the addition of all the area loads multiplied by inclined plan area is going to give us total load, and either that load will be on intermediate panel or it will be on end panel. Based on that, divided by 2 value can be adapted for your intermediate or end panels. The next factor is live load. So for live load calculation you need to refer IS 875 part 2, and that gives live load condition for inclined roof trusses. Now these particular inclined roof trusses classification of load depends upon axis provided or axis not provided. If the axis is provided and the sloping angle is equal to 10 degrees, in that case is 1.5 kN per meter square of plan area is to be considered. And if the angle is greater than 10 degree, So for every degree after 10 is increased, 20 Newton per meter square load is to be deducted. So likewise, two condition, access provided and access not provided, likewise calculations can be done for live load, and again it will be your plan area or plan load. Now third important load, which is the main deciding factor for the design, is wind load calculations. Now basically wind load calculation depends upon the geometry of your building, the three dimensions, length of building, width of building and height of building. Based on these factors only the wind force acting on elements can be calculated. So according to 875 part 3, for wind load calculation, force on individual member, that is chord members, is given by difference between the coefficient CPE minus CPI into area into PD. Now this particular area is the inclined area as wind forces are acting perpendicular to member. So inclined area into design wind pressure PD. Now one by one we'll see these factors. So Cp is factor for external pressure coefficient, Cpi is internal pressure coefficient, inclined area is meter square value, so chord length into spacing of your purlins, spacing of your trusses, and Pd is the design wind pressure in kilonewton per meter square. So initially we'll see external pressure coefficient Cpe. So this external pressure coefficient depends upon H by W ratio of building. So that is height of building to width of building ratio. And according to table number 875 part 3, table number 5, you can calculate the external pressure coefficient. External pressure coefficient is classified initially based on H by W ratio. Secondarily, it will be classified depending upon the inclination of principal rafter. At what inclination your principal rafter is inclined, according to that your forces will be defined. And thirdly, it depends upon windward direction or leeward direction. So the amount of force acting on the elements is towards windward side or leeward side. Depending upon that your calculation will be dependent. So that is given in directly IS 875 table number 5 part 3. You can directly check where this particular value will be calculated. Similarly, internal pressure coefficient for normal permeability. Now internal pressure coefficient depends upon the amount of opening for building. What are the percentage of opening is there. So if that particular opening is a normal condition, in that cases your factor of internal pressure coefficient is to be considered twice as plus minus 0.2. So value is to be calculated or formed for a plus 0.2 as well as your minus 0.2 value. So this is as per as 875 part 3. Now out of this formula, force is equal to CPE minus CPI. These two factors we have seen. A is the inclined area and PD value is remaining. Now for inclined area calculation, you should observe this particular figure. So inclined area is nothing but this particular from the support to up to the perpendicular drop from your purling section, that is to be considered. Now next, inclined area is calculated using spacing of truss multiplied by panel length of principal rafter, in plan inclination. So design wind pressure now design wind pressure is given as 0.6 Vz square. So this is the formula as per 875 part 3. Design wind pressure Pz is 0.6 Vz square. Now where Vz is what? This is design wind velocity. So design wind velocity is given in meter per second at particular height Z, and the wind force acting on the building is considered only if the height is greater than 10 meters. Below 10 meter we are not going to consider the effect of wind forces. So now design wind speed Vz. So for design wind pressure Vz, as per IS 875 part 3, we are requiring these particular four factors. Initially your VB value, that is basic wind speed, then K1 factor, K2 factor and K3 factor. So these are the factors required for calculation of Vz, and Vz square will be multiplied with 0.6 in order to get your Pz value. Now if Pz is known, that is nothing but PD. Area is known to us, and difference between the external and internal pressure coefficient is going to give us force acting on the member. So your basic wind speed VB, that is to be calculated from appendix A of 875 part 3 clause number 5.2 from page number 53, and where the list of major cities and towns in India are given, and according to that your value will be considered. So ready value is given, either you may refer the graph or you may take the value directly from appendix A for VB value. Then next is K1 factor, and K1 factor is called as your risk coefficient. Now basically risk coefficient depends upon the life or design life of your building. design life of building and basic wind speed. If the design life of building is greater, the factor multiplied will be greater. So for example, as per 875, the design life are as general building 50 years, temporary building 5 years, non-hazardous building 25 years, and important structure that is 50 years. So if the classification is mentioned in your examination, you consider acknowledge this and select the value of risk coefficient K1 factor from table number 1 page number 11. So it is given in table number 1 page number 11. Similarly, for second factor K2 factor, that is terrain height and structure size factor, you have to refer table number 2 page number 12. On table number 2 page number 12, the classification is initially given according to terrain category and class of building. So initially we will see the category. There are four types of category: category 1, category 2, 3 and 4. So category 1 stands for number of obstruction and average height of obstruction. If the number of obstruction around your building to be constructed are very less and its height is less than 1.5 meter, in that cases that particular land is going to come under category 1. While in case of category 2, there are few number of obstructions with average height greater than 1.5 meter up to 10 meter. In case of category 3, number of obstructions are available and average height is greater than 10 meters. While in case of category 4, the number of obstructions are greater, or even some skyscraper or a multi-story buildings are available nearer to building. So these particular terrain categories are what? These are reducing the impact of wind force on building. So for example, terrain 1 or category 1 is going to have worst effect on your building. Similarly, category 2 will be having somewhat less. Similarly, category 3 will be having less than 1 and 2, and category 4 is the most simple case on which wind effect on your building is going to be reduced or lesser one. So in short, these factors are reducing as the category is going to increase. So that is first thing. Then next is class of building. Now class of building depends upon the dimension of building. You need to identify the greatest dimension of building. Usually building is having three dimension: width of building, length of building, height of building. Out of these three dimensions, which is the most biggest or greater dimension that is to be considered? So in case of class A building, the dimension, greatest dimension is up to 20 meter. If the class B type of building is there, in that cases the dimension will be 20 to 50 meters. And third class case or class C, when the dimension of your building or greatest dimension of building is greater than 50 meters. So likewise you can define what is the class and terrain category of building, and you can calculate K2 factor. Now third factor remaining, that is K3 factor, and it is called, also called as topography factor. So topography factor details are given in appendix C page number 55 for different cliff escarpment on wind. Usually this particular factor is having value of 1 to 1.36 maximum. If your upwind slope or any escarpment cliff is near to your building and its slope or its inclination near to your building is greater than 3 degrees, in that cases only this particular factor is required. Now if the first condition is there, if the angle is less than 3 degrees, the value is equal to 1.0. If the angle is greater than 17 degrees, in that cases the value is going to be 1.36 compulsorily. And if the upwind slope is in between 3 to 17 degrees, in that cases you are requiring one factor, and that factor is called as Z by L factor. So Z by L factor is nothing but, here Z is nothing but it is the height of your escarpment, and L is nothing but it is the distance of your building up to the point where your height is measured. So likewise horizontal distance, Z by L ratio is to be calculated, and based on that your K3 factor will be determined. So importantly to remember from this is K3 factor. K3 factor depends upon upwind slope. Usually upwind slope value is not mentioned in the numerical. In that cases directly you may consider K3 factor equal to 1. So likewise by calculating K1, K2, K3 factor as well as your VB, your VZ will be calculated. After calculating VZ, go for VZ square into 0.6, you will get PZ value, that is design wind pressure. If PZ is known and you have calculated with CP and CPI, area and PD is done, or PZ is known, you can calculate the individual force acting on the industrial building. So likewise your forces, different forces acting on your building will be calculated, and according to this your panel point load calculation for dead load, live load, as well as your wind load will be calculated. Now in case of your calculation for wind forces, either the force will be two types, that is positive force when the direction of forces is towards the truss, or it may be negative when the direction of force is away from the building. And now these calculations usually depends upon CPE factor, that is table number 5 of IS 875. According to that, dimensions will be designed. If the force is negative, this negative nature is away from the building. If the nature is positive, it is towards the building. So if all these forces are calculated, you may calculate it with the member forces, and if design force table is completed, you can start with the design of members. So thank you very much.